All right, we're back with the second half of the first lecture from part 3, and we're going to be talking about neural networks. So the neural network is essentially a means of doing machine learning, and as we've discussed, it's a way for a computer to learn to perform a task by analyzing training examples. Now, the neural network is modeled loosely on the human brain, and it's basically a neural net consisting of thousands, if not millions, of simple processing nodes that are interconnected. Now, most of today's neural networks are organized into layers of nodes, and they feed forward, meaning that the data moves through them only in one direction. In this slide, it goes from left to right. And the individual node might be connected to several nodes in the layer beneath it from which it receives data. So in this case, the hidden layer in the middle is receiving data from the layer on the left. And then the hidden layer is then connected to the layer on the right or above it, which is, and can be connected to several nodes once again. And this is where it sends its data. Now, to each of its incoming connections, a node will assign a number, which is the weight. And when the network is active, the node receives a different number, a different data item, over each of its connections and multiplies it by the associated weight. And then it will add the resulting products together, yielding a single number. And if this number is below a threshold value, the node doesn't do anything. It stays quiet. So it passes nothing to the next layer. But if the number exceeds a threshold, then the node fires, and which in this case is what we call here the activation function. And the sum of the weighted inputs is then sent along to the next layer. Now, in the case of a feed-forward backpropagation net, as we have here on the slide, what's happening here is that the backpropagation training algorithm subtracts the training output from the target, which is your desired answer, to obtain the error signal. And this is where you have here on the right, you have your loss function. It then goes back to adjust the weights and biases in the input and hidden layers to reduce the error and thereby improving your algorithm. You can imagine that this process cannot just be done in one single iteration, but it is repeated many, many times in order to get the best model. And this is where you have what's called epochs, where you, or epochs, sorry, where you have iterations of going forward and then back in order to improve the model. So every epoch that you perform is going to be hopefully a slight improvement over the last one. Also, when you're dealing with images, for instance, which is a lot of data, you can't just feed all of it in all of the images that you're from your training set into a single processing unit. And so what you do is you batch your data into smaller batches and feed it in that way. And basically, so your batch size, is used to separate the data into smaller units to reduce the load on your GPU. And in this case, one epoch is counted when all the batches have completed, and then you have a whole bunch of epochs to move forward and improve your model. Here's just a more detailed slide on a neuron or node, which is made up of the linear combination of the inputs and the weights that later couples with the activation function. So what about those activation functions? They basically reflect the behavior of the neurons with respect to specific inputs. And if you consider the activation functions that will exist in the nodes in the middle layers, here are 6 examples of these possible functions. There's a nice figure to show you the relationship. And just to let you know, ReLU, R-E-L-U, it tends to be the most popular choice for activation function in the middle layers. I'm not going to go into detail as to how these functions work, but you can just imagine it is what determines the threshold for activation of your node. Now, how about the activation functions for your last layer or the output layer or your fully connected layer? If you're dealing with a regression, then it tends to be, or the most used activation function is linear because it's the most simple. Whereas if it is a classification algorithm, then one tends to use the softmax activation function. You can see at the bottom of the slide and at the previous slide, there's a link here that can help you make up your mind as to which activation functions you'd like to consider for your algorithm. Now you'll remember when you switch from a feed forward to a back propagation algorithm that you calculate the error, and you will do so using a loss function. The error will simply be the differences between the prediction and the target or your ground truth. Now, a very simple example of a loss function when dealing with classification, a binary classifier, would be to round the predictions to 0 or 1, and then sum the number of correct predictions over the total number of predictions. So in this case, for instance, your error would be 2 over 9. Because I have 2 incorrect predictions, and you can see that with the red arrows, over a total of 9 predictions. As you can imagine, there are many different flavors when it comes to loss function, and you will need to tailor your loss function to the algorithm and the data that you're working with. Typically in regression, there are 2 loss functions that are used most often, and that is the mean squared error, and this one will penalize you more heavily for outliers. The mean absolute error is the opposite. It tends to be more robust to outliers. When dealing with classification, if you're using a multi-class classification algorithm, you tend to use cross entropy. If you have a binary outcome like yes, no, you would use the binary cross entropy. And if you would like to penalize for when you have uncertain predictions from your algorithm, then you would use the hinge loss function. So you'll remember that once we've batched our data and we perform the feed forward followed by the back propagation algorithm, and we do that numerous times. Each time is called an epoch or an epoch, depends if you're in the United States or in England or Canada. I guess here we're supposed to say epoch, I guess. Anyway, the loss function is basically, when you calculate your error, is basically a surface. And what we're trying to do every time we go back and forth and back and forth and back and forth to improve the algorithm is we're trying to find the minima for best performance, which means that you have the most accurate algorithm with the smallest error. So how do we optimize this process of batch size, for instance, for the data, coupled with the number of epochs that you're going to go through, which are basically iterations where every time you go forward and then you come back when you've learned your error or you've determined your error and you want to change the weights in order to improve that. Well, you can imagine that you can do this very quickly or you can do this very slowly, and this is called the learning rate. So how much do you want to change between each epoch? Do you want to make small changes or large changes? And that's what this learning rate is. So small learning rate means it's very slow, but the problem is you may not find the minima. A big learning rate means fast, you're making big jumps, but you may jump over the minima. So the solution, which most people use, is called adaptive gradient. So we've seen in the previous slide with the learning rate that your situation, so your current iteration, will determine what you do next, right? And depending on your learning rate, you will make a change from your current situation to the next iteration. And so what if you were to go to the next iteration and you have a gradient of 0? So meaning no change, because you've, let's say, fallen into what's called a local minima. Then you have nowhere to go, and because of your learning rate, you're in a gradient of 0, and so you're not going to move. So one way to remedy this is to use what's called momentum. And this is where the algorithm will remember its last step, and then in order to avoid these local minima, it will add a proportion of it to the current step. And so that in that way, if your algorithm is stuck in a flat region, or what would be called a local minima, or something small that's insignificant, you can continue or get out of it and continue towards the true minima. So pretty much, when performing the gradient descent, the learning rate measures how much the current situation affects the next step, while the momentum will measure how much past steps will affect the next step. Now, of course, it would be possible, but probably not advisable to do all this yourself. And so people have put together what's called optimizers that that take into consideration your learning rate and your momentum in order to provide you with the best solution without falling into local minima. The most used recommended optimizer is the adaptive momentum optimizer, which is short form is called ADAM, so the ADAM optimizer. There are other ones that are used for specific situations, but in general, from my experience anyway, the ADAM optimizer is the way to go. So let's go back to deep learning a little bit. Now, we've mentioned before, if you look at the artificial neural network and you start adding more middle or hidden layers, that we are now into deep learning. And so by adding more layers, we increase the possibility, we increase the possible number of approximations, but we are also adding complexity to our algorithm. So with complexity comes the problem of having to be able to successfully train your model. If your algorithm is more complex, typically you're going to need more training data, and more training data means that you need a more powerful computer and GPU in order to do the processing. Of course, the payoff is that deep learning algorithms can automatically learn features from your data without the need for the prior definition by experts. Now, of course, probably the best example of deep learning architecture is going to be the convolutional neural network, which is what you use in order to develop a computer vision algorithm. Now, convolutional neural networks, of course, are made up of many, many, many layers. That's the whole point for deep learning. And those layers, there are many categories. And here are probably the top 8 most common layers that you're going to see in the convolutional neural network. The order of these layers are going to depend on how you build your architecture. Of course, you'll always start with an input and you'll end up with a fully connected, but what goes in between can vary a little bit depending on the flavor of the CNN. So we're going to talk about these different types of layers in the next slides. So following the input layer, we will have, for instance, an image that is 5 by 5 pixels, as represented here on the slide. And the next layer is the convolutional layer in our algorithm. Now, to convolve means to go around. And in this case, what we convolve with is a filter, which is basically a set of learnable weights. And we do this, so this filter is like a flashlight, for instance. And in this case, we have a 3 by 3 pixel beam, if you wish, for your flashlight, and it will convolve around your image, extracting characteristics. So you can think of the filter as storing a single template or pattern, and you can have, of course, multiple filters that will convolve around your input, which is your images, extracting characteristics. Now, within the convolutional layer, you're going to be extracting information for each filter that you're gonna run over your images. And each filter will result in information. And so the convolutional layer will extract a lot of information and typically will extract redundant or insignificant features. And so the pooling layer gives you the opportunity to reduce this information and thereby reduce the space and the computation time required for your algorithm. Now, there are several ways to do pooling. The typical examples is max pooling or average pooling, and we're not going to go into the detail here in this course, but just suffice to say that this enables your algorithm to run more efficiently. Now, after each layer, you have an output, right? So you have an input to the layer, and then you have an output to the layer that leads to the next layer. Now, if you normalize your output, so meaning you put everything onto the same scale, this will allow your algorithm to learn better, more easily, and more efficiently. And so this is the batch normalization layer that is incorporated into your many layers included in the CNN. So the next layer is the dropout layer. And what we're doing here is we're disabling some neurons with a specific probability p. Let's say, for argument's sake, a probability of 0.5, right? And what this does is it allows the network to learn different paths for the same solution. Because each time you go through an epoch, you're going to disable potentially a different neuron, a different set of neurons, and therefore it will learn different paths to the same solution. And what this does is it helps ultimately your solution from overfitting the data. Now next is the activation function layer. As we discussed earlier, when we're talking about a node and the activation function of a node, we have here the same thing, but as a layer, like as an entire layer. And in this case, as I mentioned in a previous slide, we use the ReLU activation function for hidden layers, and then the softmax or linear activation function for the final output layer. Now, once we have all the feature extractions, that's a lot of information, and we are going to need to make a choice. We need to decide on the classification. We need to make that prediction. And we will do this by using a flatten layer, which will transform the matrix that we're currently working with into an array for the fully connected layer, which is the last output layer. And here we are at our fully connected layer or dense layer, which we are going to use to make our prediction, to make our choice. In this case, with a multi-level categorical variable, meaning that there are many classes in order to predict. This slide is a great overview of the convolutional neural network architecture, which is made up of all the various layers that we just described. You'll see on the far left the input layer, which is basically your image, and is followed up by a combination of layers that will make up your feature learning, which is your convolutional layer, followed up by an activation layer, and then a pooling layer. And what this does is it takes, once your filter convolves around the image and you have multiple filters, that's what's going to give you your depth of that box, the first box you see in the convolutional layer. The depth represents the number of features that have convolved around the image, and as because your filter is, let's say, 3 by 3 or whatever, 5 by 5 or however big you want to make your searchlight, if you wish, your beam. What results once it convolves around your image is a smaller matrix, right, of output, and that's why the box is a little smaller than the image. And once you pool, it gets even smaller, but your depth remains in terms of the number of features, the number of the template or the patterns that you're looking for that are represented by the features. More and more as you go through this convolutional and activation layer followed by pooling, you keep repeating that, you end up with a very deep representation of features that you can then flatten and then fully connect and make your prediction. Let's say in this case using softmax if you have a binary classifier. Now this brings us to the end of lecture 1 where we focused on detection. And in the next lecture, we are going to talk about characterization and monitoring. See you there.